Okay, so we talked about sending video data over IP. We want to be talking about how we get video timing over IP. So how do we achieve synchronization between multiple devices on our network? And remember, when we're talking about AV, we've said there's data, timing, and a shared interpretation. And we've already covered the data aspect, so now we're specifically talking about timing over IP. So let's just recap for a moment. When we're talking about video timing, there are three aspects that we need to be aware of. There's frame rate, how quickly the frames advance. There is phase, the exact time when each frame should be displayed. And then there's raster timing. So within a frame, at what point are we sending particular pixels? And actually, we've already covered that last one in terms of raster timing when we were talking about 2110 sender types. So the 2110 sender type tells us when we have to send packets onto our network. And because those packets contain pixels, by extension, we've already agreed exactly when we're going to be sending particular pixels across the network. So that aspect of timing is already covered. So now we need to focus on frame rate and phase. If we were doing this with baseband, we would probably be using genlock to synchronize devices together. And genlock gives us not only that frame rate information, but also the phase information. So it gives us the exact rate at which we're trying to display our video frames, but it also tells us the precise instant at which each is supposed to be shown. If we're going to do this over IP, well, we're going to need to do it a different way. And 2110 essentially splits this into two parts. So the first one is to say we are going to synchronize time across all the devices on our network. The second part then is to say, okay, we also need to agree on a phase reference. So we'll look at each of these in turn. So first of all, how do we synchronize clocks across our network? Well, 2110-10 says we should use what's called PTP, or Precision Time Protocol. And it's a bit of a grey area in the standard because depending on exactly which clause you are reading, sometimes the standard says you should do something, which is standard terminology for saying this is our recommended approach, but it's not mandated. And then in other places it says you shall do this, which is again standard terminology, this time for saying this is not optional, you must do it. Now in practice, PTP is pretty much universally employed to maintain synchronization between senders and receivers. So, what does PTP actually do? Well, a PTP system typically starts with a PTP grandmaster. This is kind of our timing reference, though our timing reference itself may choose to take a steer from somewhere else. So GPS, for example, is a common way of getting a really good reference because the GPS satellites have atomic clocks. That information can be transferred very cheaply into our PTP grandmaster, and wherever you are in the world, you can synchronize your PTP system to those atomic clocks. So that's great. Now, we're obviously going to talk in a moment about how this works across a network for IP devices, but you may also have some existing baseband devices and you want those to be genlocked to that same timing reference. So a lot of video-centric PTP grandmasters will also provide conventional genlock outputs that you can use with your baseband devices. We're more interested though in terms of what goes on the network. And essentially that PTP grandmaster is going to transmit time information onto your network through the network switch and onto all the devices that you have on your network that support PTP. Hopefully, all your 2110 devices will support PTP, whether it's a source like a camera or a sink like a monitor or indeed a Brompton LED processor. And our intention here is that we need to synchronize all of these, the standard says, to within a microsecond, which is simultaneously both quite a short period of time, a millionth of a second, but also, actually, when we're dealing with such high video resolutions, it's quite a long period of time. A microsecond is the amount of time it takes us to send thousands of pixels. So actually, it's not as stringent as it could be, but it is nonetheless what the standard says, so that's what we work with. How do we use this then to synchronize frame rate and phase? Well, we've said that PTP is used to synchronize the exact time across all of our devices. And that means that we're going to agree what the time is right now, but we're also going to agree what the time is in a moment. And what that means is that we are also agreeing how fast time is advancing. And if we're agreeing how fast time is advancing, then provided both sender and receiver know what frame rate we are wanting to achieve, 60 frames per second, for example, well, now, because the clocks are synchronized, they both have the same concept of what a 60th of a second is. So great. We are now in agreement in terms of how quickly we should move from one frame onto the next. This gives us our frame rate, but it doesn't give us our phase information. And for that, our devices are going to need a shared reference point. And the way that 2110 addresses this is it actually references SMPTE 2059, which is the standard that says, okay, we are going to define what we call the SMPTE epoch, which was midnight on the 1st of January, 1970. And what that effectively means is that whatever frame rate you're choosing to run at, there was a video frame at that precise moment in time. So at 60 frames per second, for example, there was a video frame then, and then exactly a 60th of a second later, there was the next video frame, and a 60th of a second later, another video frame, and so on, and so on, and so on, up to the present day. So everything is referenced back to that original time point, 1st of January, midnight, in 1970. So that gives us our reference point, and 2110 essentially says, well, we are expecting all of our streams then to adhere to that phase. It does allow us to specify a phase offset for an individual video stream, but it's fixed, essentially, so it can't drift around. So, when we're talking about video timing, we've said there are three aspects. There's the frame rate, and we've said we can cover the frame rate over IP using PTP. Let's all agree what the time is, how fast it's advancing. We then have the same concept of what that frame period is. We also then need to agree on phase, and the way that we agree on phase is by referencing back to the SMPTE 2059 epoch. And then there's raster timing, so within a frame period, when are we sending pixels, when are we not sending pixels, and that's all down to the 2110-21 sender types. Are we narrow linear, or are we a wide sender? So that gives us what we need in terms of our timing. We've talked about how we send data. We've now also talked about how we send timing information over an IP network. So we've now got two of the three things that we need, and in a moment we'll move on to looking at the third aspect of this, that shared interpretation and how that might work over IP.